Today we're going to be categorizing chemical bonds based off of their electronegativity difference. So I'm going to be abbreviating electronegativity difference as E.N.D, but let's go back a little bit before we get there. So elements gain and lose electrons to become stable. We learned that when we talked about the octet rule. This is actually what forms a chemical bond. Now, the type of chemical bond, there are three that we're going to have to worry about, a fourth and a fifth eventually, but for now it's just the main three. And these are going to be the big three because the other ones we don't really do much with. So we can categorize bonds based off electronegativity, which is the atom's magnetic pull or hold on electrons. So if you think of an atom as a mini magnet, it's going to make this much easier. So the nucleus, think of it like this. We have a nucleus, and the nucleus has a positive charge. And then you have the orbitals, and they have electrons, and the electrons have negative charge. The atom attracts, well, the nucleus and the electron attract to each other, but it doesn't just end there. The nucleus of one atom can actually attract electrons that are from different atoms because it's that strong or sometimes that weak depending on the atom, and that's what is going to be causing, that's what electronegativity is. It's the atom's pull on its own electrons and other electrons from other atoms. So it is both in this case. It ranges from 0 to 4. I don't know why they chose 0 to 4. They could have chose 0 to 10, but 0 to 4 is what someone chose at some point. So 4 is the strongest, 0 is the weakest. If an atom had an electronegativity of 0, that means it wouldn't be able to attract its own electrons at all, and those electrons would essentially just float away. So no atom has an electronegativity of 0, but they do get close to it. And last but not least, in the case of noble gases, they do not have electronegativity. And the way I'm going to say it is that atoms only pull on electrons if they need electrons. Okay, and so noble gases won't attract electrons because they don't need any. So we'll just say that they don't have so when you look up noble gases on the periodic table, rather than saying that their electronegativity is a 0, it's just going to have a dash. So it's not going to have a number, which means they don't have it. And as far as we're concerned, that's the truth. So the way you do this is pretty simple. You look up the electronegativity of the two atoms in the bond, and then you subtract. And if the difference between the electronegativities falls into these three categories, this is what type of bond it is. So if the difference is 0, that means the two atoms are going to attract the electrons at exactly equal amounts. Therefore, the electrons are going to end up being shared equally in the middle. It is what is called a nonpolar covalent bond. The only time this happens is when you have two of the same element bonded together, and you should know this already, but the saying Brinkelhoff, B-R-I-N-C-L-H-O-N-F, those are the only elements that do this. So the first scenario we're going to talk about only happens when you have these elements bonding with each other. So to draw it out, here's what it would look like. Fluorines are 2,7, which means they have 7 valence electrons. Now, normally you would put a dot on every side, and then you'd go around again for the second dot. I did it in the reverse order because I knew the answer ahead of time. So when these two make a bond, they're going to share their electrons. The way I'm going to show that is by using a circle. The way we clean that up is it looks like this. The circled electrons become the line. The unshared pairs don't. They get written in, and it's going to look like that. Done. It's that easy. A quick way of figuring out if your electronegativity is 0, you have a nonmetal bonding with a nonmetal, and they're the same. So F with F, same element. That's how you know you're dealing with a nonpolar covalent bond. And what nonpolar covalent bond means is simple. Covalent means they are sharing valence electrons, which they are, and nonpolar means there's no poles, like positive and negative ends, like the north and south pole of the Earth. So there's no poles here, so it's just that. Obviously, when we get to polar covalent, we're gonna have to add something else in, but I'm gonna save those for last because they tend to be the most complicated. All right, next one. If the electronegativity difference is greater than 2, we have what's called an ionic bond. The reason it's an ionic bond is because ions are formed as a result, hence the name. The electrons get transferred. So what this means, And if we draw this out, sodium has 1 valence, chlorine has 7. What this means is that the electronegativity difference is so great between these two elements that sodium's hold on its valence electron is so weak, chlorine's is so strong that as a result, they don't share. Chlorine literally rips away the electron from sodium, and so sodium loses it completely. All right, and that's it. And the reason we do this is because of the octet rule. I'll go back and talk about it on the other one. I guess I forgot to mention that. But if you look at it, sodium's 281. It needs to lose 1 in order to become stable. So by having it ripped away by a chlorine, it's going to lose the 1. It's going to become 28. Chlorine's 287. It gains 1. It becomes 288. Everybody's happy. How do we draw it? Well, we use an arrow to show transfer. And the way I draw the actual bond is pretty simple. Sodium lost its valence electron, it gained a +1 charge. No dots around it. Chlorine now here I'm going to use an X to show the extra electron, just something different so that just to make it a little bit more obvious. I could have made this one an X up here as well. I chose not to. And then chlorine gets a -1 charge. Now, this is not enough, because what we need to say is we need to say that these electrons belong to chlorine and they are not sodium's electrons. So just like if you have property and you say, all right, this land is mine and it's nobody else's, how do you symbolize that? Usually, people put up a fence. And so here, we're going to put up brackets. And these brackets say these electrons belong to chlorine, they're not sodium's. What holds this bond together is literally just the positive and negative attraction to each other. Once they do their exchange of electrons to become stable, they end up getting stuck together because now the pluses and the minuses that they created attract each other. Going back real quick to the nonpolar covalent, the reason they share their valence electrons is simple. They're both 2,7, so they both need to gain 1. Neither one of them is strong enough to pull it away from the other, so therefore they have to share it as a result. So this fluorine has access to 7 of its own plus 1 that it shares, and this fluorine has 7 of its own plus 1 that it shares. So it ends up looking like that. The way to tell about the ionic bonds, like a quick way to know if it's ionic, metal, non-metal. You always have a metal and a non-metal. We will go into more detail with that in a second. And then the last one, unequal sharing, or what we call polar covalent. So that's when the electronegativities are not the same, so we don't have an E.N.D of 0, and one atom isn't so much stronger than the other atom that it can pull the electron away. We have what's called unequal sharing. So this one, unfortunately, chlorine's not strong enough to rip it away from hydrogen, and neither is hydrogen to do the reverse. So they have to share. So I circle them. The fact that I put the valence electron up here doesn't matter. I could have put it on the side if I wanted, or the bottom. It doesn't really make a difference as long as there's only one. That doesn't really matter. And you circle them. Now when I clean them up, the 2 circled electrons become the line. And there we go. We are almost done. Now here's the problem. If I looked at this one and I looked at this one, I would say, well, they look the same, so there needs to be something different about this so that it's not confused with the nonpolar. And that is where the last part comes in. So it turns out if we look up the electronegativity, I'll show you how to do that in a second. The electronegativity of H is 2.2. The electronegativity of Cl is 3.2. So Cl is stronger. It is going to have the electron closer to its side, making it partially negative. Now that's different from ionic. In the ionic, the chlorine was so much stronger than the sodium that it ripped it away and it wasn't sodium's property anymore. Here they're sharing, they are just sharing unequally, and therefore chlorine gets it more than hydrogen. So what I do is I use an arrow like this, and I make the tail of the arrow like a plus sign, and what that's telling me is that this is the negative end of the molecule. The chlorine end is negative, and the hydrogen end is positive. And the quick way of knowing that you're dealing with this type of bond, two nonmetals and they're different nonmetals, and you're almost always going to have this type of bond. And that's it. Now, I'm going to show you how to do some practice problems, and we are going to categorize them not off their elements, but rather we're going to do it in the beginning off their electronegativity differences. And then as we get faster and better at this, we will then categorize them based off their element type. And there's a reason you need to know how to do it off E.N.D. And the reason is actually simple. If you want to compare if you have two bonds and they're both considered polar covalent, and I asked you which one is more polar covalent than the other, right? You would have to look up their electronegativity differences, do the subtraction, and then figure out the answer, figure out which one has a bigger difference. That one would be more polar. Or if I could give you a question where I say, based off these E.N.Ds, which one is most likely an ionic bond or a polar covalent bond or something like that. So you do have to be able to do it E.N.D way, but eventually we'll switch straight to the element type, which will make things a little bit faster. So the first thing you do is you look up the electronegativities in your reference table on the very back of the table. So if we go to the very back of your reference table, we get to table S. Table S has a category. It's right here called electronegativity. So there's the electronegativities for all the elements we're going to need. The element names are right here. The symbols are here, the atomic numbers are here, and the names are here, so I don't care how you identify it. And then these are the electronegativities, and if you notice, the ones with dashes are going to be the noble gases because they're not zero, they just don't have electronegativity because they don't need electrons. So here's what we do. We look up the electronegativities, and we write them down. So sodium, 0.9, chlorine, 3.2, hydrogen, and then the next one is 3.2 again. I'm gonna skip H2 because I already know the answer. It's technically 3.2 and 3.2. CNO, that's going to be 2.6 and 3.4. I'm gonna skip chlorine, and then there's a reason why. And KBr, 0.8 and 3.0. And then what I'm going to do for the E.N.D is I'm going to subtract it, make it a positive number. So we always keep these positive. We don't have to worry about negatives. And then just write it down. So for the first one, it's going to be 2.3. The second one, 1.0. The H2 and the Cl2 are going to be 0 because they're two nonmetals and they're the same. That's why you can quickly identify them and even skip steps there. The next one is going to be 0.8, and the KBr is going to be 2.2. And then the last part, bond type. Based off of what range this falls into, you will get your answer. So for the first one, it's greater than 2 or more. So those two are ionic. The ones in the middle are polar covalent, which means they have poles or positive and negative ends, and they are covalent, which means they are sharing their electrons, but they have poles. So sharing electrons, positive, negative ends means polar covalent, whereas the nonpolar means there's no pluses and minus ends because their sharing is equal. Last bit. So these guys are going to be and the last step, rank in order of polarity. Polarity can also be called, polarity has another name. It's called ionic character. It means the same thing. It just means how positive and negative your ends are. So the way you do it is simple. The largest E.N.D is the most polar, second largest, third largest, fourth largest, and the zeros happen to be tied for last, so we're going to say that they have the exact same polarity. So all I'm doing is ranking them based off largest E.N.D to smallest E.N.D. Just be aware that I can't do that until I actually have the E.N.Ds.